All right. Work with variable forces. All right. Since we've already discussed the definition of work, this is going to be the point-by-point definition of work. So, as an object moves through space, at any point along its path, the force that it is experiencing could end up changing in its size or direction. So force is actually position dependent and can end up pointing different ways. The displacement can also end up changing its direction to follow a curving path as something moves through space. So these little green colors are going to be dRs. Our position vector through space as an object moves following a complex path, whereas the white ones are more showing which way the force happens to be pointing at any given moment, which is not necessarily the same thing. So if you want to find the work in a case like this, where the force varies in size and direction and the displacement is variable, then you need to use an integral. Okay, so the work is equal to the integral of the force vector dot product with this infinitesimal displacement vector dr. Now that's the proper way of doing it. If we're lucky, then the directions of these things are fixed. So if directions are fixed for f and dr, then you can write the work is equal to the integral of magnitude of the force times dr with the cosine theta brought outside. Okay, this is probably the most common way of dealing with it. Spring force kind of works this way. You pull in one direction, the force is in a particular direction. Usually you're pulling along the same direction as the force, so if you're calculating the work done by spring force, it ends up being relatively simple. And as a matter of fact, we will touch that right now as a quick example. So, consider elastic force. Okay, we need to introduce elastic force, so I guess the title of this should include that. I'll have to remember that when posting it later today. The elastic force is stated to be minus kx in the I hat direction. So if you have a spring and you pull on the spring will pull back on you. That'll give the elastic force. Can't remember if we use FE or FS, but it differs based on which class I'm teaching. So one class will have to adapt. All right, so here we've got our spring, we stretch it, there's an elastic force pulling back as we pull to the side. It's a very interesting force. You see it has the minus sign. So if this point right along here is x equals 0, and x equals 0 is where the spring is stretched, and uncompressed. In other words, it's the magic point where you get 0 force from the spring, or another way of thinking about it, it is the natural length. Okay. So as we proceed to stretch this in the positive x direction, we'll get a force back in the negative x direction. If we compress it in the negative x direction, we get a force due to the spring in the positive x direction. This ends up looking something like Fe on the y-axis, x on the x-axis, and we get something that goes through the middle looking, well, like a straight line. Now that's an ideal spring. An ideal spring has no mass. No mass. And no elastic limit. What is an elastic limit? Well, if you take a real spring and you stretch it really hard, it permanently changes its shape, and that permanently deforms it, and you don't get this curve anymore. So for relatively small forces, relatively small amounts of compression or stretching, the spring will return to its natural length consistently every time you release it. If you overstretch or overcompress a spring, it may not return to its original length. But this gives us a force that depends on x and is along the x direction, and it is variable in size. So we're going to try and calculate the work done by a spring when the spring is forcibly stretched or compressed by an external force. All right, so in that case, work will be equal to an integral over minus kx in the I hat direction dot product with, we'll have just dx in the I hat direction in this case. So let's calculate the work done if we start at some x naught and we end at some xf. All right, we've got a dot product here, which is the simplest possible case. We're assuming that they are along the same direction. If it turns out that's wrong, the integration and our limits will handle it, so we're not going to touch it. So handling the dot product, we end up with kx dx because they're along the same direction I hat. Integration limit is from x naught to xf. All right, the minus k can come out in front. We have an integral of x dx that's going to become x squared over 2. So we have 1/2 kx squared evaluated between x naught and xf. Oops, I forgot my minus sign. There it is. Minus 1/2 kx squared limits x naught to xf, which means the work in stretching a spring is minus k over 2 x final squared minus x initial squared. Okay, in a later section, we'll talk about how we can use this fact to get the potential energy in stretching a spring, or compressing a spring for that matter. Okay, but there is a quick, simple example, and we've covered 2 topics, work for variable forces and the spring force, at least a brief introduction to it. All right, I think that's going to be it for this one. There will be some practice problems you can try at this point in the practice set, so feel free to take a look at those. If you're catching this when I'm recording the videos originally, there may not yet be videos showing examples, but in future classes those will also appear.